Okay, hello everyone. Good evening. So can someone just let me know if I'm audible or not, and whether the screen is visible or not. Good evening everyone. Good evening. Am I audible? Is everything working fine? Is the setup working fine? If everything is working fine, we can just move ahead. Okay, fine. Voice is too low. Okay, I'll just try to increase the input level. Okay, how is the voice now? I just hope that it's better. Okay, good evening everyone. Fine, so we'll just get started, and I'll right away move to the slide where we actually left off. Fine, so actually in the last class we were discussing about this thing, about circular linked list, and I told you that doubly circular linked list is, although not in our syllabus, or I would say that not many questions have been asked on doubly linked list, doubly circular linked list, but still I wanted to discuss doubly circular linked list structure and a few basic questions of doubly circular linked list with you. So actually the structure of a doubly circular linked list node is same as the structure of doubly linked list node. Fine, so the structure of node is actually same. So we are basically having a pointer to the next node, and we are having a pointer to the previous node, and along with that we are also having the data stored. Okay, still my voice is low. I don't know why is that so. Pratibha Sahu probably has some issue with my voice, but in case everyone else is fine, then probably I cannot really do much about this. Okay, if I am not audible, actually what happened, I'll try to increase the input levels. I just hope that there is some difference now. Okay, fine. Okay, fine. So the structure is somewhat the same. Fine. So the structure is the same as doubly linked list, structure of the node. And if I discuss about the structure of the linked list, then in my doubly linked list, the next pointer of the last node and the previous pointer of the first node are actually pointing to null, right, in my doubly linked list. But in case of circular linked list, these two pointers are also utilized. So the previous pointer of the first node actually points to the last node. So basically the previous pointer of the first node points to the last node, and the next pointer of the last node points to the first node. Fine, so this is my head of the circular linked list, doubly circular linked list. Fine. So actually this thing so now we can right away access our last node, the address of our last node. In all the other nodes, be it circular linked list, or in singly linked list, or in doubly linked list, if we are having the address of the head, then also we were not able to access the last node directly, and we had to traverse the linked list. and we had to traverse the nodes one by one so as to get the address of the last node. But in case of doubly circular linked list, I can right away get the address of my last node. How? I'll simply do head previous, and this will give me the address of the last node. So that is why many of the operations for insertion at the end and let's say deletion at the end, this can be done in order of one time. So basically there are a few like operations which can be performed in a very optimal way in case of doubly circular linked list. So I'll now discuss the insertions, the different insertions and the deletions in doubly circular linked list. Okay, Priyam, the last class was held yesterday only. Okay, so I'll just discuss about this thing now. Fine. So we actually need to discuss this, that how do we do the insertion at the beginning. Fine. So I can get the address of the last node. So how can I get the address of the last node? It is actually equal to the previous of the head, right? So I can have the address of this particular node. Fine. And I also have the address of this particular node, and let's say if I have to do the insertion in the beginning, then there are mainly 4 pointer changes, I guess, that we need to make. So let's say if I have to make or insert a new node at the beginning, then what will I have to do? I'll have to change the next pointer of the last node. So the next pointer of the last node, so this particular pointer will now not point to head, it should point to the new node. Fine. And also the previous pointer of head, should now point to the new node, and it should not point to the last node, right? So I'll say that the head previous should now point to the new node. So after making these changes, I also need to make the 2 pointers of the new node, the next pointer and the previous pointer, I need to make them point to the right node. So the new node's next should point to head, right? So I'll do that. So new node's next should be pointing to my head, and my new node's previous should point to my, where should my new node's previous point to? It should point to the last node. Fine. So basically all these operations, and my head would now be updated. So my now head is actually now equal to new node. So basically all of these 4 pointer changes and this particular step and this particular statement can be executed in a constant amount of time. So that is why the insertion at the beginning takes only constant amount of space, and insertion at the end is also somewhat the same, because if you are inserting at the end, that would mean that you are inserting a new node after this particular node, right? So all the steps for insertion at the end will be same except this particular step, that my head will not be updated. Fine. So insertion at the beginning is actually equivalent to insertion at the end in case of doubly circular linked list, except this particular thing, that my head is not updated. Fine. So after like getting done with this, we'll discuss insertion in the middle. For insertion in the middle, it will take order of n time. So I'll just show you why. Because let's say if you want to like insert a new node over here, then you would want to get the address of this particular node, right? So and how do you get the address of this particular node? By traversing the whole linked list, which will take order of n time. Fine. So insertion in the beginning, insertion in the beginning and insertion at the end takes order of 1 time, whereas insertion in the middle takes order of n time. Fine. And in case so now I'll just rub this off, so you can like take a note of this, that while doing insertion at the end or insertion in the beginning, I actually like we updated 4 pointers. So you should not really cram this up, and you should more try to understand it as to why we changed these 4 pointers. So in case you are like able to get that idea, you'll be very easily able to like answer different questions in exam. Fine. So now I'll just show you that how do we do the deletion. Fine. So if I have to do the deletion at the head, then I need to have the address of my last node, and as we guys know that we can like get the address of the last node in order of 1 time. How? Last node is actually nothing but it is the previous pointer of the head. So I can get the address of my last node. So now I can do the deletion at the beginning in a very easy way. How? I'll simply have to update the last node's next pointer, and it should now point to heads next. So now, so let me like just make this particular linked list a bit more clear. Fine. Fine. So once I have got the address of the last node, which 2 pointers do I need to update? I first of all need to make this last node's next pointer point to this particular node, right? So I need to basically update this particular pointer. So my last node's next pointer, where should it point to? It should point to heads next. Fine. So this is the one pointer change that I had to do. So now it will point to here. And what is the other pointer change that I need to do? That for this particular node, its previous pointer should no more point to head. Its previous pointer should now point to the last node. Fine. So for this particular node, so for second node, and how can I get my second node? It is heads next. So heads, so for this particular node, its previous pointer, where should it point to? It should point to the last node. So simply by making these 2 pointer changes, I was able to make, so now I can simply do free the head. Fine. Free the memory which is allocated to the head, and now you can like update your head also. So like you can do all those things, but the thing is that these are mainly the 2 pointers that you need to update. So in order to like make it more clear, what I can do is that I'll first get the address of the second node also. So I can simply say that second node is actually equivalent to my heads next, and then second node's previous. So I basically just updated these 2 pointers. One was this one and the other one was this one. Fine. So basically just by updating 2 pointers I was able to do the deletion at the end. So basically this particular procedure also take order of 1, and similarly deletion at the end also can be done in order of 1. Fine. So I'll not show you how because that would take some time. And for the deletion at the middle, so let's say if you want to delete this particular node, you would actually want the address of its previous node. And how can you get the address of the previous node? For traversing. So that is why deletion in the middle will take order of n time. Fine. So that is all about doubly circular linked list. So now we'll actually discuss a few things about, or a few questions about, linked list. So in a circular linked list organization, insertion of a record involves modification of how many pointers? So I'll just draw a circular linked list and we can then answer this particular question. So this is my circular linked list, right? So now let us say that I have to do an insertion. So let's say I'm doing an insertion over here. Then how many pointer changes do I need to make? First pointer change would be that for this particular node, its next should point to this particular node, and for this particular node, its next should point to this particular node. So basically there are 1 and 2 pointer modifications that I need to do in case of insertion of a record. That is why I've been discussing, I've been stressing a bit on because this thing that how many pointer changes are happening, because in exam I've seen a few questions in which they are right away asking that how many pointer changes are happening. Fine. So you you can get, you need not cramp it, but all you need to do is that get the idea behind it, the basic idea. Fine. So now let us say that I want to do the concatenation of 2 lists. So I'm having 2 lists. This is my one list and this is my other list, and I want to concatenate them in order of 1 time. Then which of the implementations of a list should be used? So let's say if I want to concatenate them then in order of 1 time. The main thing is that I want to concatenate them in constant time. Then which of the linked list representation should I use? So basically I'll take all the representations one by one. So let's say if I'm taking singly linked list representation. So if I'm taking singly linked list representation, then in order to concatenate these 2 linked lists, I'll have to, so this is head 1 and this is head 2, head of the linked list 2. So let's say if I want to concatenate these 2 linked lists, then I need to change the next pointer of this particular last node of my linked list 1. But then how will I get the address of this particular linked list or node? How will I get the address of this particular node? By simply traversing my linked list, which will require order of n time. So this particular concatenation in case of singly linked list cannot be done in order of 1 time. For concatenation of 2 lists in case of singly linked list, it will take order of n time. Fine, because we have to modify the next pointer of the last node, and in order to get the address of my last node, I'll have to traverse my linked list, which is an order of n operation. So now let us just take doubly linked list. So now if I take the example of doubly linked list, fine. Then in case of doubly linked list also, I'll actually have to modify the two pointers. The first pointer is my next pointer of the last node, so the next pointer of the last node should point to this particular node. And as we know that in order to get the address of my last node, in case of doubly linked list also will require the traversal of the whole linked list, which can only be done in order of n. And the other pointer change that I need to make is that head 2's previous pointer needs to be changed, but I am already having the access or the address of the head 2, right? So this particular thing can be done in order of 1, but updating the next pointer of last node will require us order of n time, because we need to get the address of my last node, fine. So in case of doubly linked list also, the concatenation will take us order of n time. Now coming over to circular doubly linked list. In case of circular doubly linked list, as you know that we can get the address of the last node in order of 1 time. In case of doubly circular linked list, we can get the address of last node in order of 1 time. How? Because last node is actually equivalent to head 1's previous in case of doubly circular linked list, right? So we can update the last node's next pointer very easily in order of 1 time only. So that is why in case of circular doubly linked list, it will take only order of 1, fine. So this is actually the right example, and there is no array implementation of lists. So so C is the right answer, fine. So now we'll move over to the next question. So the next question says that in worst case, what is the number of comparisons needed to search a single linked list? Actually, this is a very important point to note down, that in case of linked list, be it any linked list, be it, let's say, it can be either singly linked list or doubly linked list or circular linked list, be it any linked list, we can only do linear search in case of linked list, and binary search is actually not possible in case of linked list, fine. And we can only do linear search in case of linked list. So I'll not be able to show you as to why binary search is not possible on linked list, because binary search actually requires you to be able to access the middle element in order of 1 time. If you are doing the binary search now, it will require you to access the middle element in order of 1 time, but that cannot be done in case of linked list, because accessing the middle element will require us order of n time. So basically, in a nutshell, binary search is actually not possible on linked list, and that is why we always have to do linear search. And what is linear search? That you will have to first check the key whether that particular element is present in this node. If not, then you check in this node. If not, then you check in this node, then you check in this node, then you check in this node. So that is why we will actually have to do basically order of n comparisons. So we will basically have to do the comparison with all the nodes, fine. Yes, and so Priyanka Tomar was saying that binary search is possible only on sorted ones. So Priyanka, in case my linked list is sorted now, then also we cannot apply binary search on that, fine. So in case of sorted arrays only, so in case of sorted array only, my binary search is possible. In case of sorted, even if I'm having the sorted linked list now, then also in that case also my binary search is actually not possible on a sorted linked list. Fine. So now we'll move over to the next question. So the question says that I'm having a singly linked list. Let P be my singly linked list. So I'll just draw the singly linked list. Okay, so it is saying that I'm having my P singly linked list. So let's say its head is over here. Now let Q be a pointer to an intermediate node X. So let's say this was the node X and we are having the address of this particular node stored in a pointer Q. Now what is the time complexity to delete the node X from the list? Let's say if I have to delete this particular node, then what is the time complexity? Actually I told you this, that if we have to delete this particular node, then we will have to modify its previous node's next pointer. But in order to get the address of this particular node, we will again have to traverse the linked list, and traversing the linked list requires order of n time. So that is why the answer to this is A, order of n. So I just hope that you have got this, that although we are having the address of this particular node, but using the address of this particular node I cannot get the address of its previous node. अगर यहाँ पर दिया होता ना कि P is a doubly linked list, if the question would have been this, that P is a doubly linked list and I'm having a address of the node which is to be deleted, then I could have got the address of the previous node in order of 1. How? I would have simply done Q's previous to get the address of the previous node. Fine. And this would have given us the address of the previous node in order of 1 time. But that is possible only in case of doubly linked list. In case of singly linked list, I cannot get the address of previous node right away and I will have to traverse the linked list, which will take order of n time in worst case. Fine. So that is why the answer to this is order of n. So now we have like discussed a few questions on linked list. So now we'll move over to our next data structure, which is stack. So stack basically follows. So I'll not like discuss much about stack, but I'll basically discuss about the questions that are based on stacks. Fine. So stack basically follows LIFO property. I hope you all guys know this, that in case of stack, whichever element comes in at the last is the element which actually is processed at first. So let's say 1 came in, then 2 came in, then 4, then 3, then 8, then 5. So let's say 1 came in, then 2 came in, then 4, 3, 8 and 5. So whichever element came at the last will be processed first. Fine. And then whichever element came in at first will be processed at the last. So you can either call it LIFO or also you can call it FILO. That whichever element came in at first would be the one which will be processed at last. So basically you should not really tell anyone that it is a FILO, but I was like just kidding. So this is basically, it follows LIFO property. Fine. And there are basically 2 operations involved in stack. One is push and the other one being pop. So push is to make an element push to the stack or make it enter the stack, and pop is to get the topmost element out of the stack. Fine. So basically I'm not going to like write the code for the implementation of stacks. I'll be discussing the like uses of stacks as to in which or problems stacks are used. So basically stacks are used in parenthesis balancing, postfix evaluation, infix to postfix, and also for like function calling stack or in recursion, as we have seen that or you might be knowing that whenever we are calling a function in my stack, there is actually a stack for function calling also. In my stack, a new activation record is pushed for every function call that I make. So let's say if I'm having a function fun and it is calling fun2 function, then first of all in my stack the activation record of fun will be pushed, and then whenever I'm making the call to fun2, an activation record of fun2 will also be pushed. So you need not like stress much on this. We'll be discussing like this thing in probably in C programming. If you have like completed C programming, you should be knowing this, I guess. Okay, so now we'll basically be discussing these three implementations of stacks. So one is the first one being parenthesis balancing, and it is actually very easy, and there is actually like not much need of discussing parenthesis balancing. So it is for parenthesis balancing, let's say they will actually give you a string of parentheses, and they will ask you whether these parentheses are balanced or not. So basically, how do you check that whether a given string of parentheses are balanced or not? For that particular thing, you will have to, for topological sorting and for finding out the connected components, yeah, we can use stack, but probably we will use see that particular thing in graphs section, that how do you find out all the connected components. Fine. Actually, how many preem was okay. So I'll like move back to this particular question. So in parenthesis balancing, we'll be using the stacks. So whichever whenever an open parenthesis is coming, an open bracket is coming, that is pushed at in the stack. Fine. And whenever, so let's say first of all this particular parenthesis came in and this was an open parenthesis, so I pushed it in the stack. Then again this came in, which was also an open parenthesis, so I pushed it in the stack. And whenever a closing parenthesis comes, I will check that whether my closing parenthesis is actually same as my top of the stack. So in case my top of the stack and my closing parenthesis are same, then fine, I'll simply pop the top of the stack. And in case they are not equal, I'll say that my parentheses are not balanced. I'll right away get out of the program or get out of the code, and I'll say that my parentheses are not balanced. So till now they are balanced, right? So because I've processed this, and when I was processing this, my top of the stack was having the open parenthesis. So now I came across this, so I pushed it onto the top of my stack. So then I came across this and I pushed it onto the top of my stack, and then I came across this particular parenthesis. So this particular parenthesis is actually a closing parenthesis. So for this thing, I'll actually see my top of the stack. Now because these two are actually not equal, the type of these two parentheses is actually not equal, so we will right away jump out of the code and we'll say that my parentheses are not balanced. So parentheses are not balanced. So fine. So if I have to write the program of this, I'll first simply make some space. So I'll just write down the pseudo code, a very simple pseudo code for this. So process every parenthesis, PAREN, parenthesis, one by one, every parenthesis p, let's say. So if the parentheses are given in the string, you actually process them or take them one by one. Now if p is open parenthesis, then you simply push it to stack. And if p is closing parenthesis, then compare top of the stack with p, and if p is equal to top of the stack, you simply pop. Else, if p is not equal to the top of the stack, you simply break out of the loop or whichever loop you had, and you simply state that parentheses are not balanced. Else, simply say that parentheses are not balanced. So this is actually very easy, but I just wanted to like state it once. So this is actually very easy. Fine. So now I'll be now discussing about postfix evaluation. So basically, first of all, before I discuss about postfix evaluation, I'll first discuss about the different kinds of expressions. So there are infix expression, postfix expression, and prefix expressions. Fine. So basically, in the mathematical world that we study about, we are basically using infix expressions only. Let's say a plus b into c divided by d. This is actually an infix expression. Or if I have to give one more example, then it would be a plus b into c e divided by d plus c. So this is a kind of infix expression. But the way computers evaluate a mathematical expression, it has to be always in the form of postfix. So whenever computers have to evaluate an expression, it always has to be in the postfix form. Fine. So that is why we have to study the conversion from infix to postfix. Fine. And then we'll see that how this particular postfix expression is evaluated in computers. So that is why these two things are important to us. First of all, that how do we convert my infix expression to the postfix expression, and the second one being that how is my postfix expression evaluated in computers. So that is why we study these two algorithms, that how do I convert infix to postfix and how do you do this particular postfix evaluation. Fine. So now I'll just erase this thing and I'll discuss about postfix evaluation. So postfix evaluation is also like very easy. Postfix evaluation is also very easy, and basically the main thing is this. The main algorithm is this, which is like relatively difficult to understand, but postfix evaluation is actually very easy. Fine. So if I have to discuss about postfix evaluation, let's say if I'm having a postfix expression a b c into plus. So this is a kind of a postfix expression, right? So in my postfix expression, basically in postfix evaluation we use an operand stack. Fine. So what do I mean by operand stack? It is simply a stack which is actually storing my operands, this a, b or c. In case of my infix to postfix evaluation, you will see that we'll be using an operator stack. That is a stack which will be storing our operators, plus, multiply, divide, and all of them. Fine. But in case of my postfix evaluation, I'll be using an operand stack. So what do I do? So I'll actually process all of my input like expression one by one. So if the element that I'm processing, element E, is operand, if it is an operand, then you simply push that operand on stack. Fine. And if the element E is actually an operator, then you pop 2 elements out of stack, apply this particular whichever operator, apply E operation on the 2 operands that we have popped out, on the 2 popped out operands, on the 2 popped out operands, and you push the result onto the top of stack. So let's say if I have to process this, because A is simply an operand, so I'll push it onto my stack. Then B is also simply an operand, so I'll push it on to the top of my stack. C is also an, so I'll like take a better example, because this is like looking relatively easy, so I'll like take a better example. Fine. So let's say it was looking 10, 12, multiply, 2, divide, 5, plus. Fine. So this is decent enough, I guess. So I like process them one by one now. So 10 is because 10 is an operand, so I'll push it onto my stack. Now 12 is also an operand, so I'll push it onto my stack. So now I came across an operator which is multiply. So now I'll pop out the top 2 operators. So 12 is popped out and 10 is also popped out. So now I'll apply E operation, whatever operation was to be performed, I'll apply that particular operation. So which is, so now I'll get some result which is 120, and I'll push that particular result onto the top of my stack. So after I popped out these 2 operands, my stack got empty, right? So now after like popping out my top 2 operands, I applied the operation, and whatever result I got, I actually pushed that particular result onto the top of my stack. Fine. So the next step is, so the next thing is, the next element that I come across is 2. So I'll simply, because it is an operand, so I'll simply push 2. Fine. So now I again need, so when I come across this particular operator, I see division. Fine. So because this is division, which is an operator, so I'll have to pop these 2 and then apply the division operator. So I'll get the result 60. So I'll push 60 onto my stack. Then I again come across this particular thing which is 5. This particular operand, so I push it onto my stack, and then I come across plus, so I simply pop them out and I get 65 as the answer. So this was like very easy, but I just wanted to like take you through this particular process. So this particular process of postfix evaluation is very easy. The main thing is this only, that how do you convert an infix expression to a postfix expression. Fine. So we'll just start off with this. Oh, sorry. Fine. Okay. So the very first thing is that we will be using operator stack. Fine. So how do we use operator stack? As to what is the procedure? So I have to convert, let's say I'm taking this particular example. So you should not really like look at this options, because no option out of this is correct. So you need not like look at this, you simply like look at the procedure that I follow. Fine. So this is actually my infix expression that I have been given, and I have to convert this particular infix expression to a postfix expression. Fine. So the procedure goes something like this. So I am processing each and every element one by one. So if E is an operand, then you simply add it to the output, to the postfix output. Then you simply add E to the postfix output. Fine. So easy enough. If E is an operand, or even if E is an open parenthesis. No. In case E is an open parenthesis, then we don't really like have to add it to the postfix output. So I'll like make a different case for this. Fine. So now if I can use else if E is an open parenthesis. If E is an open parenthesis, then add open parenthesis onto the stack, I should say push my open parenthesis onto the top of the stack, or I can simply say push the E. Fine. So I'll like make it look easy, and I'll simply write push E, because E is an open parenthesis, right? Then you simply push E. And in case else if my E is a closing parenthesis. So these three cases are like very easy. The main case would be the fourth case that I will like just discuss. So the main would be that if E is an operator, that is the main thing that has to be discussed. These are like very secondary things, but still I am discussing that. Else if my E is actually a closing parenthesis, then keep popping out elements out of stack and add them to output, postfix output, if or until you see open parenthesis, until you get open parenthesis in the stack. Fine. Until you get open parenthesis. So in case I am getting a closing parenthesis, then you keep popping out operators. I can, instead of elements, I can write keep popping out operators out of the stack and keep adding them to the postfix output until you get an open parenthesis. Fine. So this particular case is main, that else if E is an operator, then what will you do? Fine. So you will actually, in this particular case, you will actually have to see two things. So it is basically going to have two more, sub cases and sub cases. So you will actually have to compare. So I'm like clearing this thing. So else if E is an operator, then basically it will have a few more sub cases. Then you simply compare. What do you compare? The precedence of E, whatever operator you came across while processing this particular input, and also you compare the precedence of the element at the top of the operator stack. So whichever element would be present at the top of your operator stack, you compare the precedence of this particular operator with the operator that you came across while you were processing the input. So if the precedence of, let's say, E was greater than, I'll make some space. So let's say if the precedence of E was actually greater than the precedence of the operator at the top of the stack, then you simply push E onto the top of the stack. Then you simply push E onto stack. Fine. So I just hope that you have taken a note of these cases. So I'll simply I don't know whether I should I'll add the rest of the cases over here. Fine, because we are running out of space, so I'll add the rest of the cases over here. So fine. So if the precedence of E element that I came across is greater than the precedence of the top of the stack, then you simply push E onto the stack. Else, if the precedence of E is less than the precedence of top of the stack, then what you do? So in case it is getting a bit overwhelming, so don't really worry. I'll solve many questions for this infix to postfix and you'll get the whole procedure. So you need not worry. So just follow along. So you don't really have to worry. You'll for sure get everything. Fine. So else if the precedence of E is less than the top of the stack, then keep popping the top of the stack operators and add them to the output and add them to postfix output and for how long do you have to do this? Until you come across the top of the stack which is having more precedence. Fine. Until the top of stack is having more precedence or the stack has got empty. Fine. Until the top of the stack is having more precedence or the top of the or the stack has got empty. So this is what you do. This is like two more cases, but there is one more case that we need to discuss. The main case is else when the precedence of my E is actually equivalent to the precedence of my top of the stack. Then what do we do? In these two cases, we have discussed this thing that if the precedence of my element is greater than the precedence of the top of the stack, and we have discussed these cases that in case my precedence of the element is less than the precedence of top of the stack. But what if the precedence of E is actually equivalent to the precedence of the top of the stack? Then what do? Then you actually do this thing that you compare the associativity. Then you actually compare the associativity, because now these two operators are same. I'm not like checking this thing, that in case they are having the same precedence, that would mean that they are like more or less same. So in that case, you actually compare or see or refer the associativity. Refer to their associativity. In case they are like left to right associative, in case E is left to right associative, then you simply pop top of the stack. Fine. Else if E is right to left, then you push E. Pop top of the stack and like add it to output. So like we have discussed a bit more of theory, so I'll like I think we should right away now move on to the question first, and then like we can like discuss about the theory, because there is not much of more of theory now. So we'll right away jump into the question. Fine. So just bear along with me. So now we'll because we'll be like discussing many questions now, so you'll automatically get almost everything. Fine. So you need not worry. So fine. So now we actually need to convert this particular infix expression to a postfix expression. Fine. So I'll write the postfix expression over here. So now this is my operator stack. Fine. This is my operator stack. So first of all, I come across A. Now A is an operand, so I'll right away add it to the postfix output. Fine. Now I come across plus. Now in case of plus, I cannot really compare its precedence to top of the stack, because there is no top of the stack, so I'll simply push it. Fine. Push the operator plus to the top of the stack. Now I come across this particular operand, so I simply add it to my output, postfix output. Now I come across this multiply. So now my E is multiply, and my top of the stack is plus. Fine. So I'll compare whether the precedence of E is actually greater than the precedence of top of the stack. Fine. So which is actually the case, right, that the precedence of E is actually greater than the top of the stack. So we will follow this particular case, and we will push multiply onto the top of the stack. Fine. Now after having done that, we will now we actually now process this particular open parenthesis. So now when we process open parenthesis, what do? We simply push open parenthesis onto the top of the stack. Fine. So now we again process the element C. Now we again process element plus. Now we again process element D, which is an operand, so I need not do anything. And whenever I come across this closing parenthesis, what do? Then keep popping out all the operators till you come across open parenthesis. So I simply pop out this, and I add it over here, and I simply pop out this. Fine. So now after having like getting done with this, I need to process this division operation. So now division, this particular operation, division operation, is having more precedence than than my top of the stack, which is multiply. So I'll simply add division over here. Fine. So now I simply process F. F will be added over here. Now I process plus. So now when I have to process, when my element E is now plus, so I simply see that whether my top of the stack is having more precedence. If my top of the stack is having more precedence, then you keep popping the top of the stack. So I pop this, and I add it to the output, and I process this also and I add it to my output because they were having more precedence. Fine. So that is why I actually like had to pop both of them out. So now the precedence of plus, which is my top of the stack, is actually equivalent to this. Okay. So now for this particular operator, this plus operator, these are equivalent. I mean, my top of the stack is plus, and the operator or the element that I was processing was also plus. Now because they are equivalent, I will actually have to abide by this particular rule. That is, I'll have to check whether they are having the same associativity, I mean which associativity are they having. Now because my element E, which is plus in this case, is having left to right associativity, then what do? I will actually pop. Where did that go? Okay. So I'll simply pop my top of the stack and add it to the output. So I'll simply pop this particular plus and I'll add that to the output. Now I'm left with this particular, I mean I'm not having any element onto the top of the stack, and I cannot really compare this particular element's precedence. So I'll simply push it to my stack, and now I process D and I add it to the output. Now I process multiply. Multiply is having more precedence, so I add it to my output. Oh sorry, now I add it to my operator stack. Now I process E. So after I'm done with this, now because there are no more elements, so I'll just empty out my stack, operator stack. So multiply comes out and plus comes out. So basically the answer is this: A, B, C, D plus F divide multiply plus D, E star plus. So basically like this particular procedure is a bit difficult to like cramp up, but if you would like know the basic meaning of postfix, now these cases would like look very easy. So I'll just try to explain you that why we are doing this. Fine. So let's say when you are like processing this infix expression. Fine. So whenever you are trying to convert this particular infix expression to postfix expression, then why do I have this particular case and why do I have this particular case? This is something that we are going to discuss. So actually these things are not important. I mean, of course they are important, but you can get this very easily. The main thing is these three cases, 1, 2 and this one, 3. Fine. So we'll discuss about these three. Now if the operator which is which we are processing right now is having more precedence, then I would want, so let's say if I am saying A plus B into C, then during the evaluation I would always want that this should be processed first. That is why whenever converting it to postfix, I should have this, that multiply should come first and then only plus should come, right? That is why whenever I'm already having plus now on my stack and multiply is coming up, then I'll push it onto my stack, so that whenever like we are performing pop, my multiply will be popped first. That would mean that multiply operation would be done before the plus operation. So like I'll not be able to explain it to that extent, but whenever you will be like sitting alone and you will be like trying to understand this thing, you will get this thing for sure, that as to why are we having all these cases. Because if you ask me, I also have never like crammed this up. I'm just writing all of this out of all the understanding that I have developed over years. Fine. So this particular cases are not to be crammed but to be understood. Fine. So now if the precedence of E is actually less than the top of the stack, let's say if it would have been A, or I would write it rather over here, if it would have been A into B plus C, then if I would have converted it to postfix, it would be A, B into C then plus. Then why so if I have to like draw an operator stack for it, then multiply will come in first over here and then plus would try to come in onto the top of it. So whenever I would be processing plus now, I would want that multiply should happen first. So that is why I'll have to pop multiply first, and then only I would want that plus should be pushed only after multiply is popped out. That is why we are like having this particular case. So I don't really know that whether I am able to like do justice to this or not, but these cases are to be understood and not to be crammed. Fine. So and in case they are both having like, let's say if they are having A plus B plus C, if they are having the same precedence, then you would always add this particular thing first, and then whatever is the output of this, then you will add this thing, right? Because their plus is having left to right associativity. That is mainly the reason as to whenever the element E is having left to right, we first pop that out. We actually, so let's say if I was already having plus and then one more plus came in, so we would want that this plus should happen first, this particular plus should happen first, only then the result of this should be added to C. So if I convert it to like postfix, I'll not do A, B, C plus and plus, I'll do A, B plus C plus. This is the right postfix conversion of this. Why? Because I want A and B to be added first, and then whatever is the result of this, then that should be added to C. In case of this particular expression, B plus C would be evaluated first, and then whatever is the result of this, that would be added to A. So this is actually a wrong postfix expression of this, and this is actually a right postfix expression of this. So that is why in case they are having the same precedence, you will actually have to check this thing, the precedence thing. Fine. So now probably like we'll solve this particular question also. So I'll just make some space and then we'll solve this particular question also. Fine. So they are saying that these all operators are left associative, that means left to right, and my power operator or exponentiation operator, what should I call it? Okay, so I'll probably like call it A raised to the power B. Okay, so this particular operator is right associative, and for the precedence, this is having more precedence than this, then this, then this. Fine. Then you have to find out the postfix of this particular expression. So I'll have my operator stack over here, and also I'll have my postfix output right over here. Fine. So now I process A and then I add it to my output right away. Then I process B, I add it to my stack. Then I process, then I process plus and I add it to the stack. Then I process B and I add it to my postfix output. Then I process multiply. Now multiply is actually having more precedence than plus, which is top of the stack. So I don't really want plus to be processed or plus operation to happen first. So that is why I'll add multiply onto the top of the stack. Then I process C, I add it to my output. Then I process minus. So whenever I process minus, minus is actually having less precedence, so I would want that multiply should happen. Fine. Now minus is actually having less precedence even from plus, even lesser than plus. So I'll actually have to pop plus also, and I'll perform plus, and then I will add minus. Fine. So now I process D. To process D, I just simply add it to the output. So now I process this raised to the power. Now because raised to the power is having more precedence, so I'll add it to the top of the stack. Now I process E. Now I again come across this raised to the power. Fine. So my element is raised to the power and my top of the stack is also raised to the power. So this is the particular case that we need to address. So now because raised to the power is right to left associative, so that is why we will actually push, right away push this particular operator. Fine. So I'll right away push this particular operator, and after processing this, I'll process my last operand, which is F, and then I'll pop all my operators one by one. So this is what the actual postfix expression is for this particular given infix expression. So the answer would be A. Fine. So this is like how do we do infix to postfix. So this particular thing is actually like a bit difficult, but equally important to understand. So in case you guys like have any problem, you can like always try to like rewatch this, and in case you'll have any problem, you can always ask me to like repeat in the next lecture also. Fine. But first I would actually want you to like repeat this thing a bit and try to solve a few questions on your own. Fine. So this is the last question on stack. Actually it is very easy, but still we'll discuss them once and then we will move over to the queues section. Queues section is not like very lengthy and we will not see many implementations or many uses of queue, but we will see only like that how do we implement queue using arrays. In this thing also I basically want to discuss a few cases only, that how do you detect that my queue is empty and how do you detect that my queue is full. So these are mainly the two cases that I want to like discuss with you in my like implementation of queue using arrays. And then you guys might be knowing this, that we can actually implement a stack using two queues, and also we can implement a queue using two stacks. So I'll discuss these. These are the only two things that have to be like discussed in queue. Apart from this, I actually like didn't come across many questions of queue which were like having any particular use case. Fine. So we'll first like just discuss this particular thing, this particular question on stack. So which of the following permutation can be obtained in the output using a stack? So they are saying that this is the string of integers that I was processing. This is the string of integers that I was processing, and I can either perform push, pop operation. Whenever I do the pop operation, that will be added to the output, this particular output, and whenever I am coming across this particular integers, I'll simply keep pushing them. Fine. So is this particular output possible? So we'll like see all these output one by one. So I'll try to like bring this particular output. So 1, so initially 1 is there, so I'll simply push 1. Then 2 is there, so I'll simply push 2. Then 3 is there, then I'll simply push 3. So now because I want 3 in my output, so I'll pop 3 and I'll add in my output, I'll add 3. Now I come across this 4, so I will push 4. So this was out of my stack, so I'll now push 4. Now because 4 is required in my output also, so I'll simply pop 4. Now I come across this particular 5, so I'll simply add 5 because I want 5 in my output. So after I add 5, I'll simply pop 5 so that it can be added to the output. Now can I get 1 as the output? I can never get, because 2 will always come before this particular output. 2 will always come before 1. So I can have 2, 1 over here, but I can never have 3, 4, 5, 1, 2. 3, 4, 5, 1, 2. This particular output is never possible. So this is actually crossed out. Fine. So this particular thing is possible, right? This is actually what we see. So answer is B. So now we'll discuss about these two options also as to why are they not possible. They are not possible. So whenever I come across 1, I push 1 and then I pop 1 because 1 was needed in the output. Fine. So then they wanted 5 as the output. So I'll push 2, I'll push 3, I'll push 4, I'll push 5 and then I'll pop 5. So I got 5 as the output. Now they are asking that give us 2 as the output. It is actually not possible. Why? Because 2 is at the bottom of the stack. So I cannot really get this particular output. So same would be the case with this thing. Why? Because 5, 4, 3 would be possible to get, but 1, 2 is not possible to get. 2, 1 is, so 5, 4, 3, 2, 1 is possible, but 5, 4, 3, 1, 2 is not possible. Why? Because let's say they wanted 5 as the output. So I pushed 1, pushed 2, pushed 3 and pushed 5 as well. Because this is the string, this is the sequence in which I have to process them. Fine. So now when I have pushed 5, I'll have to pop, because I want 5 in the output. So I'll have to pop 5. So in my output, I'll add 5. And then I'll pop 4. So in the output, I can add 4. Then I'll pop 3. In the output, I can add 3. But now I cannot have 1 in the output. 2 will always come before 1. So this particular 5, 4, 3, 1, 2 is actually not possible. Fine. So this particular thing is very important, but I just wanted to discuss with you. So probably we'll wrap this particular session or this particular class over here only. Q will actually not take much time. Now the things we are actually left with in this particular data structure course or the data structure subject is mainly graph and hash table. Hash table will not take much time, it can be done within half an hour at most. And this particular thing will actually take 1.5 hour for sure. So I'll actually have to take one more class. So I'll probably check with Abdul sir and other educators on Acadflix if they are having any class scheduled or what is their timing, and I'll let you know guys that when we can schedule this extra class, we can say, because we have to cover graphs and hash table. Fine. And then we'll mark data structures as complete. Fine. So Khushbu, I'll actually let you know that if we can have data structure class, because actually we are tomorrow we are going to have 2 classes for crash course, and also there is one more class for complete course. Fine. So that is why I'll have to check with the educators that whenever, like when will they be free, so that I can also, like, because I also have to like go to office, and if I like get some time, get some mutual time, then I'll for sure let you know. Fine, so I'll discuss with them and let you know. So thank you so much for joining in, and I'll meet you in one more class for data structures, and then we'll, after that we can like jump to algorithms. Fine, so thank you so much for joining in, and good night.